In this video, I'm going to read through a relatively new paper. It's pretty much fresh off the press, called Overtrained Language Models Are Harder to Fine-Tune. This is a new type of video I'm doing, which is just a paper reading video. I wanted to read more papers and I wanted to make more videos, so I thought I'd combine the two forces. And this is a 72-page paper, but the body of it is 12 pages, and that's what I'm going to focus on. I've also started a Claude project, and I've given Claude this PDF. And just as a sanity check, I asked it to summarize the paper's findings. And yeah, based on what I read in the abstract, I think it looks pretty good. Obviously, we'll go into more detail. And then I have Google open so I can look things up. Usually I look up papers that they reference in related work. So yeah, let's just walk through this. Large language models are pre-trained on ever-growing token budgets under the assumption that better pre-training performance translates to improved downstream models. In this work, we challenge this assumption, show that extended pre-training can make models harder to fine-tune. So that is definitely noteworthy, leading to degraded final performance. We term this phenomenon catastrophic overtraining. So new term just dropped. For example, the instruction-tuned OMO 1B model pre-trained on 3 trillion tokens leads to over 2% worse performance on multiple standard LLM benchmarks than its 2.3 trillion token counterpart. Through controlled experiments and theoretical analysis, we show that catastrophic overtraining arises from a systematic increase in the broad sensitivity of pre-trained parameters to modifications. So a systematic increase in the broad sensitivity of pre-trained parameters and modifications. So not sure what that means. Sounds important and kind of core to their work. Our findings call for a critical reassessment of pre-training design that considers the downstream adaptability of the model. All right, so I'm not going to read word by word, so it's not going to be a verbatim reading, but in some cases it will be. They talk about the two-stage paradigm where we have pre-training on a vast corpus of uncurated data, followed by post-training on high-quality task-specific data for downstream tasks like instruction following, multimodality, or reasoning. More data is better. Massive investments in scaling have occurred. A compute optimal ratio of roughly 20 tokens per model parameter. So that's interesting. I was not aware of this number. And if we look at the Hoffman paper, I'm not sure I've seen this one. Oh, I guess I have. Oh yeah, this is the Chinchilla paper. Okay. I haven't read it, but I saw it referenced in the small LM2 paper, and I've heard of it, but we'll go back here. So 20 tokens per model parameter, yet recent models have far exceeded this. Llama 2.7 billion was 13 times the recommended ratio. So 1.8 trillion and 7 billion. So 1.8 trillion divided by 7 billion is 257. If we divide that by 20, we get 13. So that's where they're coming with that. Llama 3, 8 billion scaled this further to 15 trillion. This trend is driven by consistent gains in zero-shot performance, with some exceptions. Scaling up language model pre-training does not universally translate to better performance after post-training. And they show theory and experiments, and they have catastrophic overtraining. Longer pre-training harms final model performance. It's not isolated. It emerges constantly or consistently across a range of models and tasks. And they've done empirical evaluations. And we're going to look at that. Looking at this here, language models with extensive pre-training can exhibit catastrophic overtraining, where the performance of post-trained models degrades as the pre-training stage is extended. So they have stage 1 pre-train for T tokens, stage 2 post-train instruction tuning, And I would assume that this tapering off is what we're talking about here. So as we go past 2 trillion tokens of pre-training, we taper off and actually decrease as we get to 3 trillion tokens of pre-training, even though the pre-trained performance increases. Okay, cool. So let's keep going. 3% worse and 2% worse on different benchmarks compared to an intermediate checkpoint trained on just 2.3 trillion tokens. And that's figure 2. So this is the same situation. I think these are, base model is dashed, fine-tuned model is solid, and what are we looking at here? Let's read this. Extending pre-training can degrade performance after fine-tuning on Anthropic HH, so that's these, and Lava, which is these. We consider fine-tuning on various intermediate checkpoints. Base model performance improves with pre-training token budget black dashed curve. So base model performance improves in all of these scenarios. Yeah, some of them it tapers off, but in all of them it keeps improving. The performance after fine-tuning drops as we pre-train on more tokens. So we see this dip, you know, so on and so forth in almost all of them. This one drops and then goes up again. This one drops, goes up again. This one drops, goes up again. Okay, so this is 2 different data sets, 2 different adaptations or, you know, desired tasks, and different benchmarks. Okay, I think that's all I want to see on figure 2, so we're going to keep going. To understand why this occurs, we turn to carefully controlled experiments. Modifying the parameters of a pre-trained model leads to forgetting of previous acquired capabilities. So that makes me think of catastrophic forgetting. The extent of this forgetting depends on the magnitude of the parameter modifications. However, so that I feel like is already known. However, another key factor influencing forgetting is what we term progressive sensitivity. For modifications of equal magnitude, models that have undergone longer pre-training exhibit greater forgetting. For modifications of equal magnitude, okay, we'll take a look at figure 4 in a sec. Catastrophic overtraining arises when this increased forgetting due to post-training modifications overtakes the improvement during pre-training. Constraining the magnitude of the parameter modifications can mitigate this, but it can also limit the capacity to adapt and learn. This trade-off shapes the feasibility of preventing catastrophic overtraining in practice. Okay, so we go to figure 4. All right, what are we looking at here? So progressive sensitivity. I think I kind of get this. I'm not really getting it. So extending pre-training progressively increases the degree to which fine-tuning degrades perplexity. So almost 30 million models trained on various pre-training token budgets are fine-tuned on downstream tasks using fixed hyperparameters. Lines connecting models sharing hyperparameters differing only in, or lines connect models sharing hyperparameters differing only in pre-training tokens. So pre-training tokens change in perplexity. Learning rates range from 4 e-6 to the dataset specific maximum. We report the difference in perplexity between the fine-tuned and pre-trained models as a function of the number of pre-training tokens. So I don't understand what the color gradient here means. I don't know what blue or purple to green means. All right, let's see. I'm going to screenshot this. Let's see if Claude understands it. And can you explain figure 4 to me? In particular, I don't understand what the color gradient means. What is the difference between the purple and green lines? And let's do concise. I don't know how many messages this is going to take up. So, okay. Each line represents models with the same hyperparameters, particularly learning rate, but trained on different amounts of pre-training tokens. So we go back to this. So here's the pre-training tokens. So these are different hypers. The color gradient represents different learning rates. Dark blue-purple lines, lower learning rates starting at 4e-6. Light green lines, top, higher learning rates up to the maximum. The y-axis shows how much perplexity increases after fine-tuning compared to the pre-trained model. Higher values indicate greater degradation. Okay, so the learning rate increases as we go up. So as the learning rate increases, the perplexity gets worse. I think that's what I'm understanding. The key insight is that for any fixed learning rate, the perplexity degradation increases as you move right on the x-axis more pre-training tokens. Kind of, right? I mean, it goes down, and then it plateaus, and then it goes up. But yeah, and I guess in some cases it goes down first. But I'm probably just nitpicking here. I think that what they're trying to show is the, what is this? 10 billion and 100 billion. So this increases. Okay. So as you train the model more, and then when you fine tune it, the perplexity gets worse. I get that, and I understand, but the part that I don't understand is how is progressive sensitivity different than catastrophic overtraining? And I think they're related, but I'm just not understanding. We'll go back. For modifications of equal magnitude, models that have undergone longer pre-training exhibit greater forgetting. So we'll get to that in a second. This demonstrates that models with more pre-training overcome increasingly sensitive to the same amount of fine-tuning, experiencing greater performance drops. Higher learning rates show more dramatic degradation. Okay, I think this part, models with more pre-training become increasingly sensitive. I don't understand that. So I don't understand the following. I'm just going to copy this. As well as the following sentence from, what is this section? Still introduction? Dang. Introduction. From the introduction. Specifically, I don't understand what modifications of equal magnitude means. Okay, let's see. Modifications of equal magnitude refers to applying the same degree of change to model parameters during fine-tuning. In the context of this paper, this means when using the same learning rate and number of update steps to fine-tune different models. Okay. So that's what they're doing here. They had the same, let's just use the link. They had the same learning rate. So each line is one learning rate. So the same learning rate has the same pre-training token, so the same number of update steps. No, that's not right. Let's go back. When using the same learning rate and number of update steps to fine-tune different models, models with more pre-training tokens experience greater degradation in performance on the original pre-training task. The authors demonstrate this by fine-tuning models with identical hyperparameters but different amounts of pre-training. Each colored line represents the specific learning rate applied consistently across models with different pre-training amounts. What they observe is that as you move right along any given line, more pre-training tokens, the degradation increases even though the fine-tuning process remains constant. See, that I don't understand. I don't understand that, right? How is the fine-tuning process remaining constant? Oh, I see. Okay. So, okay, I got it. All right. Okay, so, all right. I was mixing up pre-training modifications and fine-tuning modifications. So, all right, let's back this up. I think I got it. Um, so they're fine-tuned on fixed hyperparameters on these data sets, right? So that is fixed. That is the equal magnitude. So the fixed fine-tuning, they're fine-tuned for the same number of steps for the same hyperparameters. So that's the equal magnitude. So even though they're fine-tuned in the same way, pre-training them longer makes the fine-tuning perplexity deteriorate. So that's why we go back to this modifications of equal magnitude. So I'm just going to put note, and I'll say modifications of equal magnitude equals fine-tuning on the same data set with fixed hyperparams, learning rate, update steps, etc. All right, so that's cool. All right, so I'm just gonna check with Claude. So let me know if I'm understanding this correctly. Modifications of equal magnitude is referring to the differently pre-trained models being subject to the same fine-tuning, LR steps dataset. Refers to applying the same fine-tuning process to differently pre-trained models. Okay, so I think that part makes sense now. We find that modifying the parameters leads to forgetting of previously acquired capabilities. And we might, the part I don't understand yet, and we might get to this later in the paper, is how is this part, how do they know how much catastrophic forgetting and progressive sensitivity contribute to catastrophic overtraining? So I'm assuming so I'll say maybe they get to this later on in the paper, but looking at this full sentence from the introduction, I don't understand how figure 4 distinguishes between the effects of catastrophic forgetting and the effects of progressive sensitivity. Couldn't the modifications of equal magnitude, which is same fine-tuning process, let me do this. Couldn't the increase in perplexity cause, what am I trying to say? After pre-training longer, due to modifications of equal magnitude, also be a result of catastrophic forgetting? I didn't word that great, but let's see. Figure 4 doesn't distinguish between these phenomena directly, it demonstrates both. Each line shows catastrophic forgetting. All delta perplexity values are positive, indicating degradation, while the upward slope of each line demonstrates progressive sensitivity. The authors established this distinction conceptually rather than visually separating them in the figure. The baseline effect could be a flat line across pre-training tokens. The progressive sensitivity is shown by the line sloping upward. Later in the paper, they they examined this more carefully through controlled experiments to isolate progressive sensitivity as a distinct phenomenon from regular catastrophic forgetting. So delta perplexity greater than 0. So that, I guess the y-intercept is catastrophic forgetting. because it's greater than 0. And then the slope is progressive sensitivity. So let's add a note here. Not sure if correct, but the y-intercept greater than 0 represents catastrophic, I don't need to put quotes, catastrophic forgetting, and the slope represents progressive sensitivity. Okay, cool. All right, we're 30 minutes in, about, and we're not moving very fast, so let's see. Okay. All right, anything else? While constraining the magnitude of the parameter modifications, it can also, okay, yeah, we saw that. Okay. We study how incremental feature learning leads to progressive sensitivity and inevitable catastrophic overtraining. Regularization can delay the onset at the cost of downstream performance. All right. Okay, so they exhibit this across different language models and tasks. They identify progressive sensitivity, and then they have a theoretical analysis. I'm not sure if I'm going to go through the theoretical analysis, which is, I think, why it's a 72-page paper. That would be my guess, but we'll see. Okay. All right, experimental setup. Okay. Open source checkpoints, 1 billion, 7 billion, and 7 billion. Post-training on intermediate checkpoints on these two data sets. Multimodal fine-tuning with lava. And then the ID performance evaluated on the fine-tuning task. Oh, I think this is in domain. And then the out-of-domain performance computed on a suite of 10 common LLM eval benchmarks covering reasoning, QA, common sense, and knowledge extraction. Further information on this, so just take a quick peek. So I think this is the checkpoints information. These are how many steps these are trained on and how many tokens. So 0.04 trillion is 41 billion and so on. The data sets that they use, the evaluations that they do, alpaca eval, VLM score, generalist evaluations. Okay, so obviously a lot more detail than that. I'm just skimming it, but let's keep going. All right, figure 2 compares the performance. So I think we already saw this, right? We saw this one here, and we saw that even though all the dashed pre-training curves increase, the solid fine-tuning curves at some point start decreasing. Okay. Okay, extended pre-training always improves base models. Extended pre-training can hurt post-trained counterparts. 3% lower response rate than the one that's pre-trained on 23 fewer tokens. Similar drop on various out-of-domain tasks. Okay, they also see it on multimodal fine-tuning. Models pre-trained on more tokens show greater forgetting and larger drops in performance on the various out-of-domain benchmarks. So I think that's talking about these drops. Okay, additional evaluations in Appendix E. So take a quick peek. Let's just take a look at one of these. So this is Olmo 1 billion post-trained on Anthropic HH. And we see similar drops. This is quite significant, or at least quite dramatic. Okay, let's keep moving. All right, Catastrophic overtraining. In this section, we dig deeper into this phenomenon to understand why and when expending more compute by pre-training on more tokens can counterintuitively degrade performance. Pre-training is the first stage in modern language model development. Before deployment, these pre-trained models are typically modified through post-training, reinforcement learning, quantization, or pruning. Extending pre-trained beyond a certain point can in fact hurt the final performance, a phenomenon that we call catastrophic overtraining. So we saw that. Oh, I haven't seen this kind of formatting in a paper, so that's cool. We call this token budget where performance begins to degrade the inflection point. Catastrophic overtraining can refer to a decrease of the pre-training performance or of the performance of other downstream tasks as pre-training is extended. It can happen across various tasks, even for the same model. All right, in the rest of this paper, we aim to answer two central questions. When and why does catastrophic overtraining occur? What factors influence the inflection point? We focus on modifying the pre-trained model by fine-tuning on different data sets. We also study a simple generic modification of adding independent Gaussian noise to model weights. We leave reinforcement learning and pruning to future work. All right, so real world settings, intuitive picture in the presence of Gaussian perturbations, and expand the fine-tuning in a controlled setup. Okay. All right. When instruction tuning on data sets, catastrophic overtraining on budgets exceeding 2.5 trillion tokens. This is observed as a decrease in domain and out of domain. So it seems like that's the inflection point, right? Same thing for multimodal fine-tuning. Performance in some out-of-domain tasks declines. In-domain performance shows no degradation at this token threshold. So VLM score. So let's go back to this. And VLM score keeps increasing. So yeah, it does not. So in-domain doesn't get affected here, even though for instruction fine-tuning, in-domain does get affected. So that's interesting. Okay. Model scale effects. Under the same fine-tuning and evaluation setups, catastrophic overtraining is not observed on 7 billion models for pre-training token budgets up to 3 trillion tokens. So let's look at one of these. And yeah, so here's 3 trillion tokens. Here is 3 trillion. I guess this one kind of happens at 2.5, but then it gets back up. Okay, so it seems like what they're saying is as model size increases, the inflection point increases. I think that's the takeaway. Would catastrophic overtraining emerge in 7 billion models at a larger pre-training token budgets? Why are certain downstream tasks more likely to show catastrophic overtraining when fine-tuning on a particular datasets? Are some fine-tuning datasets more likely to induce catastrophic overtraining? We build an intuitive story about catastrophic overtraining by studying a simple setting in the next section. All right. We documented several instances in real-world scenarios. We investigate a simpler controlled setup described below. Their checkpoints were publicly available. Each training budget corresponded to a different final learning rate due to the annealing schedule. Let's do that again. I don't get that. So note that our real-world experiments used publicly available checkpoints from a single training run. Okay, which meant that each pre-training budget corresponded to a different final learning rate due to so because there is a learning rate schedule and they're using different checkpoints from the same training run, learning rates, the final learning rate will be different. So they're trying to remove that confounding factor. All right, so we pre-trained models from scratch from 15 million to 90 million parameters, from 4 billion to 128 billion token budgets on C4 web data. We train with a cosine annealing schedule that anneals every model to 0. We present the results from the 30 million model and Appendix F as the other ones. We fine-tune the pre-trained models, various classification and language modeling datasets, QA, sentiment analysis, math, and code. And we also consider a simple modification of adding Gaussian perturbations to the pre-trained weights as a warm-up in section 3.3. I don't really understand this, so we'll see what that means. Our intuitive picture views post-training as some modifications to the pre-trained model that is trained on large amounts of broad data. Modifications can inadvertently distort pre-trained knowledge, leading to degraded performance on out-of-distribution or unrelated tasks. All right, let's take a quick peek at this. Fine-tuning can distort pre-trained features and underperform out-of-distribution. All right. Okay. We evaluate real-world benchmarks in section 2. We focus on measuring C4 perplexity as an indicator of how the knowledge is preserved. A decline in C4 perplexity may signal a loss of this knowledge, potentially resulting in both out-of-distribution performance degradation due to forgetting or distortion. We also measure in-domain performance as perplexity on held-out set from the same distribution. We use perplexity rather than accuracy as it is a smoother and less noisy metric and can often offer a better measure of quality than accuracy. All right, so here we go. We take base models pre-trained to various token budgets and add Gaussian noise of the following form. So we have weights, base model weights plus epsilon, where epsilon is this Gaussian noise. And I guess gamma is their hyperparameter, where sigma is the covariance matrix of the initialization distribution of the parameters prior to pre-training, and gamma controls the magnitude of the perturbation. First, we plot the change in C4 perplexity due to Gaussian noise, the difference between C4 perplexity of the base model and the perturbated parameters in figure 3. We observe an interesting trend as we track the change in perplexity between the base model and the perturbed model as a function of the number of pre-training tokens. Progressive sensitivity to noise. For a fixed magnitude of perturbation, the change in perplexity between the base model and the perturbed model increases monotonically with the number of pre-training tokens. All right, so I think we're seeing the same thing here, where instead of learning rate, we're now changing gamma from 0025 to 04. So I think that gamma is the, I don't know, would that be like the standard deviation? Or yeah, I'm not entirely sure. Let's do a new chat. Can gamma be understood as standard deviation? Yes, it can be understood as controlling the standard deviation of the noise. Epsilon is random perturbation following a multivariate normal distribution. The covariance matrix is gamma squared sigma. Gamma acts as a scaling factor of the covariance matrix. If the covariance matrix is the identity matrix, then gamma would directly represent the standard deviation of the noise added to each parameter. In more general cases where covariance matrix has a different structure, gamma still controls the overall magnitude of the perturbation. Gamma appears to be a hyperparameter that controls the strength of the Gaussian perturbation applied to the model weights. Okay, cool. All right, so as gamma increases, the perplexity gets worse, and then as pre-training token budget increases, the perplexity gets worse. Except, what's going on here? What's on the right? Progressive sensitivity of Gaussian perturbations left. Extending pre-training progressively increases the degree to which a Gaussian parameter perturbation degrades perplexity. Catastrophic overtraining right. Eventually, this leads to overall worse pre-training perplexity. We perturb almost 30 million models trained on various pre-training token budgets with Gaussian noise scaled by the factor gamma, which is the color of the lines. The left plot shows the difference in perplexity between the perturbed and unperturbed models, while the right plot shows the absolute perplexity of the perturbed models. So, oh, I see. So this is not delta perplexity. So the delta perplexity is between the perturbed and unperturbed models. So base model is a straight line, which is 0 delta perplexity. And then okay. All right, hold on. This feels like important to this distinction between progressive sensitivity. No. So this is not catastrophic forgetting, this is catastrophic overtraining. Eventually this leads to overall worse pre-training perplexity. So it does. Interesting. So all of these models, perplexity gets worse, but after a certain inflection point, perplexity gets better, it decreases, but then after a certain point, starting with a certain gamma, the perplexity gets worse. And this is saying that the difference, even though the perplexity gets better for this orange line, it is worse perplexity than the base model. So let's go back to this one. Nope, not that one. This one. Are you talking about figure 4 or something else? Or figure 3. Figure 3 is one of those controlled experiments that helps isolate progressive sensitivity as a phenomenon. They use Gaussian noise rather than fine-tuning. This provides more controlled setting. Left plot shows increased sensitivity to the same perturbation magnitude as pre-training increases. Right plot shows how the sensitivity eventually outweighs the benefits of continued pre-training. By using random noise, they can rule out that the effect is due to specific properties of downstream task and show that it's a fundamental property of the pre-trained models. So, are you saying that figure 3 Gaussian noise perturbations is absent of catastrophic forgetting because the model is not learning real knowledge and is instead getting its weights changed by random noise. Gaussian noise modification has no learning objective. So it's not catastrophically forgetting. It's purely testing how robust the model is to random parameter changes. There is no task-specific forgetting since the model isn't learning anything new. It's purely measuring how perturbation resistant the parameters become after different amounts of pre-training. The left plot shows that for the same perturbation magnitude, any single colored line, models with more pre-training experience greater degradation. That's the progressive sensitivity in isolation. The right plot then shows how this sensitivity eventually leads to catastrophic overtraining, where models with more pre-training plus perturbation perform worse than those with less pre-training plus perturbation, despite the base models continuing to improve. Okay, I think that makes sense. The one thing I'll say is, how does the model know it's not learning anything new? From the model's perspective, wouldn't a change in its weights, even if random, potentially cause catastrophic forgetting? Do they evaluate catastrophic forgetting for Gaussian noise perturbed models later in the paper? This model doesn't know it's not learning anything new. That's precisely the point. From the model's perspective, any weight change can cause forgetting. What makes this experiment isolate progressive sensitivity is that it applies identical random perturbations to models at different stages of pre-training. Since the perturbation doesn't target any specific knowledge, differences in degradation can be attributed to the model's increasing sensitivity to parameter changes rather than task-specific interference. This paper doesn't specifically evaluate catastrophic forgetting for Gaussian perturbed models separately because the entire perplexity is representing a form of forgetting. The crucial insight is that this forgetting increases with pre-training over time, or with pre-training time, even when the perturbation magnitude remains constant. This supports their theoretical explanation that longer pre-training leads to parameters that become more precisely tuned and thus more fragile to any modification, whether purposeful or random. This model doesn't know it's not learning anything new. That's precisely the point. Yeah, I'm not quite getting it. So, viewer, to make sure I'm explaining what my confusion is. Okay, so progressive sensitivity. I think the progressive part is that the longer it's pre-trained, the worse this gets, right? Okay, all right. I think I'm getting this. All right, so here's what I was arguing. It's like, is this a form of catastrophic forgetting, right? So if we think of these Gaussian perturbations as okay, if we think of these Gaussian perturbations as a form of learning, right? It's like, it's not really learning something, it's just random noise, but if we it's like a proxy, or it's like a replacement of fine-tuning. Oh, okay, so I think, let me ask this. Let's zoom in on this part. Is it fair or correct to say, let's just say, is it correct to interpret the attached figure as follows? The upward trend, higher gammas resulting in greater perplexity degradation, is the catastrophic forgetting component of degradation, whereas I'll say the upward trend for a given pre-training budget, token budget, higher gammas resulting in as you go up vertically, is the catastrophic forgetting component of degradation, whereas the upward trend given a constant gamma, higher pre-training token budget, results in greater perplexity degradation, is the progressive sensitivity component of degradation. Oops. Okay, yeah, well, I think I gave it the figure, right? Yeah. No, I didn't. Where is it? Yeah, I did. Okay. Yes, that's correct. Your interpretation captures the key distinction. Catastrophic forgetting, the vertical increase in perplexity degradation as gamma increases at any fixed pre-training token budget. Higher perturbation magnitude, greater forgetting. Progressive sensitivity, the rightward upward trend for any single color gamma value. More pre-training tokens, greater sensitivity to the same perturbation magnitude. This design isolates progressive sensitivity by showing that identical perturbations, same gamma, cause progressively more damage as pre-training increases, independent of the absolute magnitude of the perturbation. All right, that makes sense. You know, I'm always hesitant with Claude because sometimes it just agrees with what you say. But I think I've spent enough of my token budget analyzing this one. So for a fixed magnitude of perturbation, so that's gamma. So this is fixed gamma single colored line. The change in perplexity between the base model excuse me, and the perturbed model increases monotonically with the number of pre-training tokens. Okay. So let's keep moving. All right, first we plot the change in C4 perplexity due to Gaussian noise, the difference between the C4 perplexity of theta and theta squiggly, or tilde, in figure 3. We observe an interesting trend as we track the change in perplexity, and then we plot the absolute perplexity. We observe that the base model's perplexity decreases with the number of pre-training tokens. So that's what we see as the downward trend here. And even for low gamma, it's downward, but then at some point, perplexity starts getting worse. All right, in this setting, catastrophic overtraining arises from the interaction between the progressive sensitivity to noise and the monotonic improvement of the base model. In this setting, catastrophic overtraining arises from the interaction between the progressive sensitivity to noise and the monotonic improvement of the base model as pre-training progresses. Early in training, the rate at which the base model improves is faster than the rate at which sensitivity increases, leading to a net decrease in perplexity even after Gaussian parameter perturbations. However, beyond a certain point, the rate at which sensitivity increases surpasses the rate at which the base model improves, leading to increase in perplexity after the perturbation. This results in a U-shaped trend of the C4 perplexity after Gaussian perturbations. So, I think what they're saying is, let's see, can I do it? What am I trying to do here? I don't know. I don't think I can do that. Never mind. So I think it's like this region is when the decrease, right? So 1, 2, 3, 4, and 1, 2, 3, 4. So that is kind of like the inflection point. So after this one, the sensitivity due to the same perturbations is greater than the decrease of the base model's perplexity. Or in other words, the improvement of the base model's performance is outweighed by the sensitivity of the model to fixed changes, where the fixed change is the particular Gaussian noise added at a particular gamma. So I think that makes sense. I think if I think about it anymore, it's going to stop making sense. So let's keep going. Tracking the inflection point. In figure 3, larger perturbations are associated with a larger and more quickly increasing degradation of the pre-training loss. Thus, the point at which the degradation from sensitivity surpasses the improvement in the base model is accelerated for larger perturbations, leading to an inflection point at a lower token budget. So, for example, a low perturbation inflection point starts later than a high perturbation whose inflection point, right? So here's the inflection point. It's going down, then it's going up. Here, it's going down, then it's going up. So, you know, there's a, 10 to 100, so 10, 20, 30, 40. So this is like 30, 40, 50, 60, so it's like 60. So it's like twice the token budget. Okay. Cool. And I would assume that's billions, right? I think that's 10 billion and 100 billion. Okay, that's good. Intuitive picture. Pre-training on more tokens improves the base model, but also makes the base models more sensitive to noise. Progressive sensitivity leads to catastrophic overtraining as the increase in perplexity due to noise eventually overwhelms improvements in the model. For larger magnitude perturbations, this degradation sets in at a lower token budget, while for smaller magnitudes of perturbations, the catastrophic overtraining may not be observed until a large token budget. So we saw that the darker lines keep going down, whereas the lighter lines get worse. Okay, fine-tuning pre-trained models. All right, so we added noise. Noise can be seen as a canonical modification. What does canonical modification mean? Excuse me. So, refers to a basic, standard, or representative type of change to the model's parameters. It represents a simple, fundamental way to perturb a model. Adding Gaussian noise is simple, well-defined, and theoretically tractable way to modify the model parameters. It's a useful baseline. Fine-tuning involves more structured updates that are guided by optimization on specific tasks. So adding noise is a controlled experiment before moving to the more complex case of fine-tuning. Okay. All right. Fine-tuning with fixed learning rate. First, analogous to how we quantify performance drop for a fixed magnitude, gamma, we similarly need to regularize the fine-tuning in some way to ensure a consistent degree of change across the pre-trained checkpoints. Fixing the learning rate is a simple and effective way to do so. While we do not provide a formal justification, we discuss our reasoning in Appendix C. Okay. We use mu-p parameterization. For each of our controlled experiments, they have 10 data sets. We tune over all specified learning rates. Okay, I'm not getting the answer there. Fixing the learning rate is a simple, effective way to do so. So I think what they're trying to say is that when they fixed gamma, they were adding the exact same amount of noise to differently pre-trained token budget models. And adding the exact same amount of noise is approximated as fixing the learning rate. Because I would assume, because in the training loop, in the optimizer step, you have gradient times learning rate subtracted from the weights. And so if you fix the learning rate, it's like adding the same type of noise. I think the part where I'm assuming it's not exactly the same is that there's no telling that if the gradient, well, maybe there is. Yeah, I don't know. Let's see. All right, let's ask this question, and then let's try to keep moving. In this section, I think what they are trying to say is that when adding Gaussian noise with a fixed gamma, they can control and add the exact amount of weight change, i.e. perturbation, to models of different pre-training token budgets. To mimic this for real fine-tuning, they are assuming that a fixed learning rate is equivalent to adding a constant amount of noise. So 1, do you agree with my interpretation of this text? And then 2, can you tell me why or why not this is a correct assumption on their part? Your interpretation is correct. In the Gaussian, they add controlled noise with magnitude gamma. For fine-tune, they use fixed learning rates. It's not perfect. Fixed learning rates do provide some consistency. Figure 8 supports this by showing that parameter distances between pre-trained and fine-tuned models are roughly proportional to learning rate. Okay, so there's something more. However, fine-tuning updates follow task-specific gradient directions. The actual parameter change depends on gradient magnitudes, which may vary across different pre-training stages. Excuse me. The authors acknowledge this is an approximation without formal justification, which is appropriate given the experimental evidence. All right, so Claude is basically saying keep reading, and let's get to it. So for each learning rate, we plot the change in C4 perplexity from the pre-trained model to the fine-tuned model in figure 4. So I think this is the one we saw. So learning rate is fixed, and in general, after a certain point, perplexity gets worse. And then as the learning rate increases, as we go upward for a fixed pre-training token budget, perplexity gets worse. All right, so let's keep moving. Try to keep this under a 2-hour video. That would be nice. In this plot, we track how the degradation evolves with the number of pre-training tokens. Larger learning rates distort the model more. So I think that's the vertical increase for a given pre-training token budget. Second, we observe a trend over pre-training tokens analogous to the behavior seen with Gaussian noise, but this time for fine-tuning. For a fixed learning rate, so a single line of one single color, the change in perplexity increases monotonically with the number of pre-training tokens. And that is seen kind of here, right? It's kind of going down, but I think the general idea is that, yeah, it increases after a certain point. Okay. At the inflection point at which sensitivity surpasses the rate at which the base model improves, we observe catastrophic overtraining. This results in a U-shaped trend of the C4 perplexity after fine-tuning figure 5 top. So this is the U-shape that they're saying. So the base model improves, but the sensitivity eventually takes over. Okay? Analogous to the Gaussian setting, since the rate of increase of degradation is accelerated for larger learning rates, model trained with larger learning rates exhibit an inflection point at lower token budgets as the degradation is more pronounced. So I think that is going back here, so like it's a little difficult to find a good example, but kind of like here it's a lower learning rate and it is a bit plateaus, and here already starts getting worse. So oops, I went back too far. In-domain perplexity, smaller learning rates generally result in less degradation. In-domain perplexity shows a different trend. Larger learning rates result in lower in-domain perplexity, though sometimes also exhibit, so figure 5 bottom. So in-domain perplexity, let's run that again. Larger learning rates result in a lower in-domain perplexity, oops. Okay, larger learning rates lower in domain perplexity. Okay, all right. So, I see. Okay, got it. So the purple lines are lower learning rates, and the green lines are higher learning rates. So in many of these cases, or pretty much all except one, and maybe this one as well, larger learning rates yield lower in domain perplexity, though we do have some U-shape action. But lower learning rate actually has a higher perplexity. So that is really interesting. This implies that tuning the learning rate can sometimes mitigate degradation only at the cost of fine-tuning performance. We explore in section 3.4.2 when tuning the learning rate to minimize the in-domain perplexity can mitigate the degradation of C4 perplexity that arises as pre-training is extended, and when it cannot. Okay, let's keep moving. So I'm not 100% sure on this, but we'll see in 3.4.2. The intuition of the Gaussian setting carries over to fine-tuning with a fixed learning rate. Pre-training on more tokens will improve the quality of the base model and at the same time make the model degrade more when fine-tuned. Beyond a certain point, pre-training on additional tokens will degrade the resulting fine-tuned model's C4 perplexity and often the in-domain perplexity of the fine-tuning task, but not always, as we saw here. All right. We showed that for a fixed learning rate, the sensitivity of pre-trained models increases with the number of pre-trained tokens. The learning rate is tuned on a validation set from the in-domain task. This tuning process may yield a different optimal learning rates across pre-trained checkpoints, which can potentially mitigate catastrophic overtraining. So tuning the learning rate can potentially mitigate catastrophic overtraining. The degradation depends on both the learning rate as well as the sensitivity. So if a model pre-trained on more tokens can admit a smaller learning rate when fine-tuning to achieve good in-domain performance, it can compensate the increase in sensitivity. So I'm a little confused about that, to be honest, because here a smaller learning rate, right? Minimum fine-tuning learning rate is purple. Maximum fine-tuning learning rate is green. In-domain perplexity gets better with a larger learning rate. But, oh, I see. So lowering the learning rate can mitigate the C4 perplexity. Let's see. Yeah, I'm not 100% sure about this. Let's look back here. For each learning rate, we plot the change in C4 perplexity from the pre-trained model to the fine-tuned model in figure 4. In this plot, we track how the degradation in C4 perplexity evolves with the number of pre-training tokens. First, larger learning rates distort the model more. So I think what I'm missing is let's go back to what I'm assuming that C4 is not in figure 5, right? This is figure 5. The C4 perplexity for the fine-tuned models, different lines representing different learning rates, is plotted. What data sets were the base models pre-trained on? The models were pre-trained on C4 web data. The author specifically mentioned this in 3.2. We pre-train models from scratch on C4 web data. They further, okay, so why are they measuring C4 perplexity for fine-tuned data, for fine-tuned models? Okay, yeah, so it is about retaining their pre-trained knowledge after fine-tuning, how well the original pre-trained knowledge is preserved. I guess the part that yeah, so I didn't really catch this while we were looking at it the first time, but I think the part that sorry, let me grab this. Here is figure 4 in which the perplexity on the fine-tuning data set is shown to get worse as pre-training token budget increases. So this is showing downstream performance degradation, whereas figure 5 is showing base model performance degradation. Figure 4 shows the change in C4 perplexity after fine-tuning. As pre-training is extended, the degradation C4 perplexity after fine-tuning. Okay, that's fine. Wait, that's not fine. Oh, I see. Okay, so I think I was misunderstanding. Sorry, viewer, if I'm confusing you, or if you're looking at this and you're like, why is he confused? But that's fine. I think what I want to do is, all right, I need to find where figure 4 is referenced. We plot the change in C4 perplexity. Oh, okay, so I think I misunderstood that. So let's do one more check of understanding. Let's go back to figure 2. For figure 5, in domain perplexity, the performance on the actual fine-tuning tasks. Okay, I see. So let me just do one more thing. Okay, now just to make sure I understand, in figure 2 attached, they are showing change in perplexity for the fine-tuned task, or on the fine-tuned data set. Figure 2 is not showing perplex. Oh, it's showing score. Got it. Okay. All right. In domain, out of domain. Okay. All right. So let's go back down here. And let's search figure 4 again. In this plot, we track how the degradation in C4 perplexity. All right, so that's interesting. So that is a detail I didn't quite think of until now. That this is showing baseline kind of pre-trained model, base model capability is deteriorating. All right, so just for good measure, these plots show that base model capabilities decrease, as well as fine-tuned task performance decreases after a certain pre-training token budget is passed. The base model consistently improves. Yep, the fine-tuned models initially improve but then degrade. The key finding, okay, so it's not quite telling me how I want to see it. I guess what I'm trying to understand is like C4, if we go to this one here, C4 perplexity and in-domain perplexity are different because C4 is the base model. So in this case, they trained, let's see, with C4 web data, right? We pre-train models on C4 web data. And they're looking at C4 perplexity. And then they're also looking at in-domain perplexity. Okay, so I'm not going to keep digging on this because I think I just enough understand it. Practice, the learning rate is tuned on a validation set from the in-domain task. We saw that. Okay, let's look at this. This smaller rate does restrict the extent of necessary parameter updates and might be insufficient to achieve good in-domain performance. This presents an interesting trade-off that we investigate empirically. We tune the learning rate to maximize fine-tuning in-domain performance. We track the optimal value as a function excuse me, of the pre-training token budget and plot the in-domain performance and pre-train perplexity corresponding to this optimal learning rate in figure 6. Okay, so almost 30 million models pre-trained with varying token budgets are fine-tuned on downstream tasks. Math, code, QA, and classification. Lower is better. We tune the learning rate to optimize in-domain performance. In-domain perplexity degrades with extensive overtraining, RTE, and TREC. C4 perplexity degrades in GSM-8K, StarCoder, MR, and RTE. Results averaged over 3 fine-tuning runs. Additional ablations in this one. So they use C4 for pre-training. Then we fine-tune on these 10 data sets. For tuning, we use a held-out validation set, but report scores on a separate held-out test set. In order to compute the perplexity for classification tasks, we compute a score for each class by measuring the length normalized likelihood of the class. We report the perplexity on generalist capability on a held-out C4 web data set. Okay, I think that makes sense. I do have to ask the question because now I don't trust my understanding. Let's do... Did the UI did the UI just change on Claude? Oh, can you explain the difference between the first row of plots and the second row of plots in the attached figure 6? Okay, difference performance metrics. The first row shows C4 perplexity after fine-tuning. This measure measures how well the fine-tuning model preserves its general language model capabilities on the C4 web text dataset that was used during pre-training. Got it. Lower perplexity is better. Second row shows the in-domain perplexity, which measures the model's performance on the specific downstream task it was fine-tuned on. For example, GSM-8K column shows math task performance, SIQA shows question answering performance, etc. Lower is better. The key finding illustrated is that as pre-training continues, both metrics eventually show degradation. Okay, so catastrophic pre-training is shown as a phenomenon both for retaining pre-trained knowledge and learning new fine-tuned tasks? I think the answer should be yes. Yes. Okay. All right. That was a key distinction that I wanted to make sure. All right. Let's keep moving. Our findings indicate that the emergence of catastrophic overtraining depends on how the optimal learning rate evolves. We conceptualize this trade-off into 3 scenarios illustrated in Figure 7. Before we do that, we tune the learning rate to optimize in-domain performance. Okay. And even then, it still degrades in some cases baseline or base model performance, and in some cases it also degrades the fine-tuned performance. Constant optimal learning rate. A constant optimal learning rate across token budgets leads to degradation in both in-domain and out-of-domain performance for large pre-training budget T. So if we look at Figure 7, tuned LR is constant with T. What is going on here? So this is large LR, medium LR, small LR, LR tuned on downstream val. So tuned LR is constant with T. So for I think each line has a constant learning rate, and in domain and out of domain at some point both get worse. All right, I think we got that. Slowly decreasing optimal learning rate. A slowly decreasing optimal learning rate may improve in-domain performance while out-of-domain performance degrades. Okay? Tuned LR decreases slowly. So in-domain gets better unless you have a large learning rate, and out-of-domain gets worse. Got it. Okay, quickly decreasing learning rate. A quickly decreasing optimal learning rate enables improvements both in domain and out of domain performance as the pre-training budget increases. Okay, so no degradation for a certain after a certain point. Oh, I see. Tuned LR decreases quickly. Okay, so we start at a large LR. I see. Okay, so start at a large, then we drop the learning rate, then we drop the learning rate. So no degradation. Interesting. And then here, large LR, we drop the learning rate, no degradation. Interesting, because within a learning rate it gets worse, but across learning rates it gets better. And here, slowly decreasing, so large LR to medium, there's no degradation for in-domain, but there is degradation in out-of-domain. Using a non-optimal learning rate to mitigate degradation. In cases where catastrophic overtraining emerges when fine-tuning with the optimal learning rate, using a non-optimal learning rate can sometimes mitigate the degradation or delay the inflection point. For example, in both cases where tuning leads to eventual degradation of out-of-domain loss, choosing to train with the smallest learning rate would delay the inflection point. However, this would result in a lower in-domain performance. In both cases where tuning leads to the eventual degradation of out-of-domain loss, choosing to train with the smallest learning rate would delay the inflection point. So out-of-domain, lower learning rate would delay the inflection point. So instead of inflection point being here, it would be, maybe here. And instead of it being here, it would be, maybe here. So that's what that's saying. However, this would also result in a lower in-domain performance. So if we look at in-domain, right, so the lowest learning rate is actually the worst here, and it's the worst here. Because we're looking at perplexity, right? Yeah, pre-trained perplexity degradation. Okay. All right, that makes sense. Regularization beyond the learning rate. For both the Gaussian perturbation and the fine-tuned settings, we have seen that larger parameter perturbations accelerate and amplify the rate at which model performance degrades. In the fine-tuning setting, the learning rate effectively controls the magnitude of the overall parameter updates. However, we expect that explicit forms of regularization to prevent large parameter updates could also mitigate or delay catastrophic overtraining. All right, we are approaching 2 hours, and I would like to keep this relatively short. All right, so let's look at the summary. I think we have a few more pages in the main body. Okay, I think maybe we'll go past 2 hours. Okay, so we have seen that large parameter perturbations accelerate the degradation. All right, so that's the earlier inflection point. The learning rate effectively controls the magnitude of the overall parameter updates. However, we expect that the explicit forms of regularization to prevent large parameter updates could also mitigate or delay. So we explore this in section 4. Okay. Overall, our experiments reveal that progressive sensitivity manifests under 2 types: unstructured Gaussian noise and structured fine-tuning. Progressive sensitivity is a universal phenomenon. For a fixed magnitude of perturbation or a fixed fine-tuning learning rate, progressive sensitivity leads to catastrophic overtraining as the degradation in performance eventually outweighs the gains from extended pre-training. So pre-training loss for base model keeps going down, but progressive sensitivity makes that U-shaped perplexity curve come into play. In practice, the optimal learning rate is tuned on the target's in-domain task, and its evolution can result in degradation either on in-domain performance or out-of-domain pre-training metrics. This highlights a trade-off in extended pre-training, where how the optimal learning rate evolves ultimately determines whether catastrophic overtraining occurs when these models are fine-tuned. So I think going back here, a large learning rate will give you a better in-domain, but will give you worse out-of-domain. Tuning it slowly gives you no degradation for in-domain, but it still gives you degradation in out-of-domain. And then tuning LR decreases quickly gives you no degradation in domain and no degradation in out-of-domain. So I would assume that this is your ideal, right? But I don't know if they're making that conclusion. Okay. A theoretical perspective of overtraining, to be honest, I don't think we're going to go through this in detail. So they examine in a simplified setting with 2-layer linear networks. We will study catastrophic overtraining with respect to the pre-training loss, focusing on identifying the inflection point. As a warm-up, we characterize catastrophic overtraining in the case of adding Gaussian perturbations. We also study a canonical fine-tuning task and determine the progressive sensitivity, and demonstrate that progressive sensitivity consistently arises as pre-training is elongated. They formalize the phenomenon. In the experiments, we had studied this trend by lowering the learning rate, but in this section we will instead use regularization as a means to prevent large parameter updates. Without regularization on the fine-tuning objective, the final model inevitably exhibits catastrophic overtraining with respect to pre-training loss. Regularization can mitigate this phenomenon, but can also degrade fine-tuning performance by limiting how well the model can adapt to the task. Okay, 2-layer linear regression, where pre-training performance improves monotonically with training time. We consider a regression problem where the data is generated by a full rank linear map y equals a pre-x for xy in some dimension d, and A is a d by d matrix. We sample x from a normal distribution. We denote singular value decomposition of A as this, U sigma v transpose, with the diagonal elements being strictly positive and monotonically decreasing. We will call these singular values the pre-training features and denote them as such. Yeah, I don't think I'm going to go into this right now because this will far exceed my token budget. Yep, I don't think so. I was curious to see these definitions. Okay. Yeah. So unfortunately, reader or viewer, this will be left to you as an exercise because this would take me multiple hours to digest. Okay, related work, loss of plasticity. The idea that more training can be harmful has been studied before, named loss of plasticity. This phenomenon refers to the degradation of the ability for a model to adapt to a new task. Mainly been studied on small models with small data sets or reinforcement learning. Okay, our work considers large modeling. We show that overtraining on generic web data can also degrade fine-tuning performance despite being expected to help. Additionally, we highlight an increased sensitivity to degradation of the pre-training loss that arises with overtraining, an aspect largely overlooked in the literature. So I think, oops, that's not what I want to do. But I think this is talking about what we were looking at here. So catastrophic pre-training is both for retraining pre-trained knowledge and learning new fine-tuned tasks. Catastrophic forgetting. Neural networks trained sequentially on tasks tend to forget prior tasks. Mitigation strategies proposed using regularization. Generative replay of previous examples from previous tasks. Maintaining a memory buffer for previous tasks. We show that catastrophic forgetting can become more severe with overtraining. Relationship between pre-training loss and downstream performance. The degradation of pre-training loss and the downstream loss may be related. Several works have tried to study the relationship between pre-training loss and their downstream performance. This one, what is this? Same pre-training loss, better downstream. Implicit bias matters for large language models. Analyze the effect of pre-training beyond conversions and suggest that overtrained models exhibit better transfer to downstream tasks. Our work considers web scale pre-training, which rarely converges in practice, so these findings do not contradict ours. Similarly, they highlight the effect of architecture on downstream generalization, scaling laws for optimal pre-training. We argue that fewer tokens can be beneficial for downstream performance after fine-tuning. Related work proposes scaling laws, but does not observe degradation with overtraining. The optimal pre-training token budget has also been studied in other contexts, which we saw here. There exists an optimal token budget for each model size. Subsequent works have extended scaling laws to broader contexts, including Scaling laws are not always optimal for predicting performance. They do not always predict downstream performance accurately. In addition, multiple works have observed the U-shaped trends. Pre-training loss continues to decrease when trained for up to 10,000 tokens per parameter. Yeah, okay. Finally, our theoretical analysis of catastrophic overtraining adopts a classical transfer learning setup based on deep linear networks. So I think that was their kind of theoretical analysis, I think. All right. Okay. So we have a surprising trend. Longer pre-training does not lead to better post-train models. Models become more sensitive to perturbations as they're pre-trained on more tokens. Degradation of adaptability is especially catastrophic when the pre-training and fine-tuning tasks are misaligned. And in such a case, catastrophic overtraining may be inevitable even if the fine-tuning process is regularized. We show for multiple pre-trained models, we leave understanding the exact pre-training settings that influence the severity of catastrophic overtraining, such as the role of the optimizer, pre-training distribution, and training objective for future work. We show that catastrophic overtraining can only sometimes be mitigated by regularization, but there may be other strategies such as data replay or LPFT. Fine-tuning can distort pre-trained features and underperform out of distribution. What is that? Our analysis suggests that the easy two-step strategy of linear probing than full fine-tuning. Okay, that's what that means, but we're not going to go into it. May help retrain pre-training performance. Distribution shifts may be useful for catastrophic overtraining. Cool. And then efforts to reduce model parameters for efficient deployment. So this should be, wait, what is this one? That's not what I thought it was. Mini CPM, unveiling the potential of small language models with scaling strategies. Small language models. In the context, we introduce mini CPM, 1.2 billion and 2.4 billion non-embedding parameter variants not only excel in their respective categories, but demonstrate capabilities on par with 7 billion to 13 billion LLMs. Our approach exhibits scalability in both model and data dimensions. We employ extensive model wind tunnel experiments for stable and optimal scaling. We introduce, that's where WSD, I've seen that before. I think that's what small LM used. Continuous training. We present dynamics. We're now able to efficiently study data model scaling law without extensive retraining experiments on both axes of model and data, from which we derive much higher compute optimal data model ratio than chinchilla optimal. I am tempted to take a look at this for, let's say, 30 seconds. All right, 30 seconds is obviously not going to be enough. All right, we will keep moving. We saw that are likely to amplify the negative effects of catastrophic overtraining, making models increasingly fragile to parameter transformations. Moreover, rising inference time costs associated with advances in inference time reasoning, verification methods, and other emerging post-training paradigms. We expect that there will be a further drive to improve the quality of post-trained models without increasing the number of model parameters, thus exacerbating catastrophic overtraining. Okay, we made it. We obviously are not gonna go through the entire appendix, but they have proofs in there for those of you who are into that. We glanced at some of these things. Oh, this was that figure 8 that Claude mentioned. Distance as measured by L2 norm between the pre-trained and fine-tuned model as a function of learning rate. More specifically, if theta pre and theta ft are the parameters of pre-trained and fine-tuned models, we plot the L2 norm between the two as a function of the learning rate. We observe that the distance between the pre-trained and fine-tuned model is not exactly, but approximately, directly proportional to the learning rate and independent of the amount of pre-training. So pre-training is the color, and so this was going back to the idea that in the same way that the gamma variable was a way to fix the amount of Gaussian noise perturbations, the learning rate is a way to fix the amount of fine-tuned perturbations, because as learning rate increases, the distance between pre-trained and fine-tuned weights increases. That's really interesting. I think, yeah, that would be interesting to look at in a real, not real, I mean, this is real, but, running our own experiments on a smaller model with a data set as we're doing ablations. That would be interesting to see what that looks like. Okay. I'm going to keep rolling. Oops. That's not what I wanted to do. All right, so these were some of the other data sets. Omitted figures about controlled experiments. Yeah, I like how they put pre-training perplexity here. I think that, and then fine-tuning task perplexity, I think that would have helped me not get confused, but maybe I still would have, who knows. That's kind of wonky. What's going on there? And that one is kind of creeping up to the top. That's interesting. Yeah, so obviously I'm not doing this justice. I'm just kind of peeking at what's going on here. Here's that phenomenon of higher learning rate improving the fine-tuning task perplexity. So that is my first reading of overtrained language models are harder to fine-tune. And I definitely enjoyed it. It really made me think and made me work. And as always, I don't feel a strong enough intuition to move forward thinking that, okay, this is now the new norm. But I think it is interesting. Things I've heard before when, doing paper reading groups, I think is, sometimes I think, how, and they mentioned this in the paper, which was like, what attributes of pre-training affect in what way? So are there methods of pre-training that are going to affect this catastrophic overtraining differently? So I think it would be interesting to see, is there something they did in their pre-training which caused this? But I mean, they picked good performing models like almost 1 billion, I forget, almost 30 million. I guess they trained that themselves. So they're taking models that are performing well and are open weights, obviously, because that's what we need to be able to do something like this. So I guess the hesitation you're hearing in my voice is like I don't know enough about this. I don't have a good enough intuition about whether this is now the new norm. And I don't really know how to poke holes in this. So that would be something where I would be interested in hearing from folks who are more knowledgeable than me about this work. So if you have any thoughts on if you want to poke holes in this, or if you think this is a really strong evidence for this catastrophic overtraining phenomenon, then please comment below, or you can mention me on Twitter or Blue Sky. But I will leave that for later. And thank you again for watching this video. And yeah, I think I'll be doing more of these paper readings. It certainly makes me think harder because we're doing this live, and that adds a little more pressure on getting things right as best as I can. So thanks for watching, and I'll see you next time.